We now know how our world ends. Our affinity with sci-fi movies, and perhaps the Bible, would point toward the big bad apocalypse. But what if we tell you that the end of the universe is no different than its inception? The James Webb Telescope has revealed that the universe has stopped expanding. Popular scientist Brian Cox made this prediction years ago. In doing so, he gave us the most realistic starting point to imagine the end of the world. We can look to light that began its journey before there were galaxies, the oldest light in the universe, as evidence. So if people don't believe in the Big Bang, the answer is, well, you can see it. We're heading towards Big Bang 2.0. Join us as we explore why the world has stopped expanding and James Webb's terrifying discovery. If we're certain about anything in our knowledge of the universe and its history, it's the fact that our very epic of existence is centralized around this event called the Big Bang. Of course, there are alternative theories that recognize the beginning of the universe, such as eternal inflation or an oscillating universe. But we're not getting into the validity of these theories today, mainly because the astronomical community has now readily accepted that our history in this universe starts with the Big Bang, and the ideas that succeed the Big Bang are also based on the same common point of the universe's birth. While the Big Bang is a common word in the theoretical knowledge of astronomy and space, we're hardly aware of the no's and the how's of the phenomenon unless you're a nerd who has spent hours watching some excellent visualization of the Big Bang. To be fair, the phenomenon was more than an explosion, or so to speak. Simply put, the Big Bang finds its origin in a single point, a point that was infinitely hot and dense that inflated to extreme lengths. All of this was when the universe was incredibly young. Believe it or not, at the time of the Big Bang, the universe was only 10 to the power of minus 34 seconds old. That is 100th of a billionth of a trillionth of a second in age. This is when the universe experienced an incredible burst of expansion, aka the infamous explosion or the inflation. During this process, the space expanded faster than the speed of light. So yeah, you wouldn't have even blinked when the universe grew 90 times in size almost instantaneously, from subatomic sized to golf ball sized. 1 second after the inflation, the universe began to cool, and that led to the formation of matter as we know it today. So yeah, as far as the timeline goes, within a second, our universe was full of every particle we've learned about in our chemistry class, willingly or otherwise. Protons, neutrons, electrons, anti-electrons, photons, and neutrinos are the legacy of the Big Bang. Magical, right? Well, figuratively, it looks like it. But our understanding of the universe's inception is highly theoretical. We've come a long, long way since the first moon landing. And since then, our technological advancement has grown exponentially. Back when scientists were studying the Big Bang only based on mathematical formulas and scientific models, they wouldn't have imagined that we'd be exploring the possibility of life on Mars. There have been some big breakthroughs in our pursuits to study the universe and explore space. Yet even then, our existing technology is pretty limited. You see, we can't recreate the Big Bang or peer back at the event itself. Our biggest piece of evidence comes from the cosmic microwave background that has allowed scientists to observe the echo of the Big Bang. While this mechanism is groundbreaking in the study of the universe, it's also theoretically limited. The biggest barrier in this particular methodology is the fact that we can't see the gravitational waves or the residual radiation that came from the expansion itself. So, while our entire knowledge rests on theoretical tenets, scientific theories have a large room to be disproved as well. Yep, we're pretty sure about the Big Bang as the concept, and how it was monumental in creating our universe. But there are some chunks of its aftermath that we've gotten wrong. And as shocking as it is, theories about our universe are largely based on data that is prone to human errors all the time. At the same time, some of our data is also highly conclusive about the Big Bang. Let's just say that at this point in time, it's not easy to disprove the theory altogether. Is our universe still expanding? In the last decade or so, our only saving grace to study the Big Bang was the Hubble Space Telescope. And now, of course, all bets are on the excellent precision of the James Webb Space Telescope. Before we got to use these powerful technological instruments, one of the biggest points of contention in astronomical study was the expansion of the universe. If you pick some science textbooks from the early 90s or so, you'd read about how the universe is widening. In other words, the universe is expanding. And that's one little scientific fact that we've held onto. But the real snafu here is that perhaps we don't understand what the expansion of the universe entails. And more importantly, we got to ask ourselves if the universe is actually expanding. Because spoiler alert, James Webb Space Telescope is telling us otherwise. Lo and behold, the universe have stopped expanding. And now, before jumping into the implications of this groundbreaking shift from our universe's trajectory, let's just talk about our understanding of this perplexing phenomenon in the first place. The most common knowledge associated with the Big Bang characterizes it as an explosion. And well, fiction and popular media have put solid imagery to this process as well. Any piece of media would depict the inception of the universe as some sort of a blast that honed tons of energy and matter just spread in every direction. Scientifically speaking, that sort of visualization isn't correct. Despite the widespread use of the explosion and inflation of the word, the birth of the universe wasn't exactly a blast. And scientists want us to correct our understanding of the universe. In NASA's own words, the universe did not expand into space, as space did not exist before the universe. Instead, it is better to think of the Big Bang as the simultaneous appearance of space everywhere in the universe. Our understanding of the phenomenon also reveals that our universe has lived through a durable cosmic period that was only disrupted by the reionization in space. Before that particular chemical conjecture, our universe was just pitch black dark. The let there be light moment of the universe only occurred 400 million years after the Big Bang. Yep, that's right. You see, the big explosion only created the basic tenet of all living beings and heavenly bodies in the universe. For 400 million years, the universe was plunged into darkness because, well, it's simple. There were no stars or galaxies. When that was rectified as clumps of gas turned into stars and galaxies, only then the universe got out of its cosmic dark ages. So, here's a little trivia for you guys. When do you think our solar system came into being if the universe was just darkness and eeriness for 400 million years? Well, our solar system was born 9 billion years after the Big Bang. So, yeah, sorry sci-fi movies, there's a huge disconnect between the so-called explosion and scientific theory. And of course, this changes everything. The way things are, our universe still exists as a single inception point. It hasn't moved or expanded ever since the Big Bang. What really happens is that space has been stretching along the time, and it carries matter with its trajectory. To put it in clear-cut words, the universe isn't expanding the way we visualize it or even understand it. It is actually the active stretching of space that precedes the expansion of the universe. We know it's a bit complicated to comprehend this, but it's also important to understand the implications of what we're about to tell you. For the purpose of this video, we'd continue to use the phrase expansion of the universe to signify the active movement of our space, mainly because even scientists are comfortable using the exact framing to describe the recent discovery made by the James Webb Space Telescope. The fact that the universe has stopped expanding is both terrifying and inconsistent with our previous theoretical knowledge of this baffling phenomenon. Because you see, before this shocking discovery, scientists were convinced that the universe was expanding at an accelerated rate than its inception. And well, they weren't wrong. With the help of the Hubble Space Telescope, scientists were able to gather concrete evidence to support their theory. So no, this isn't the case of NASA correcting its earlier understanding of the universe's expansion. Whatever that's happening to our universe, it's entirely new and possibly irreversible. While the discovery itself is profoundly frightening, it isn't overly unexpected either. As we talk more about gravity, you'd see that our universe was always susceptible to a recollapse. In the case when the universe had an ample amount of energy density, its expansion would stop entirely. By the looks of it, our universe is going backward. Back in the 1990s, NASA and its credible scientists had some very conclusive ideas about the expansion of the universe. The most fundamental unit of their scientific understanding was gravity. While that much still remains true today, we've some entirely different ideas about the speeds at which our universe expands. As we've already discussed earlier, scientists had a theoretical prediction about the universe's recollapse that would cease the expansion as we know it today. But also, the contesting idea was equally terrifying, if not jarring enough. Too little energy density would mean that our universe would never stop expanding. The uncharted bizarreness of the idea is quite limited today. But you see, it was the 1990s, and scientists had little technological help to find tangible or observational data for their predictions. What they were certain about was that as our universe ages, gravity would definitely decrease the rate of expansion all over the course of time, of course. And even intuitively, it makes sense. Gravitational pull brings galaxies together. This is something we've already established. So, as the universe would expand, the gravitational force would resist widening the distance between the heavenly objects. Since our universe is just a patch of matter, of course, the attractive gravitational pull would keep the matter intact. This theory was also extended to understand the rate of the universe's expansion. Scientists believed that since gravity is the binding glue for all of the matter and has existed since the universe's inception, the rate of expansion had to slow down. Sure, we didn't have any means to observe this phenomenon or carry out some big data testing, but theoretically, this made complete sense until it didn't. In 1998, the invention of the Hubble Space Telescope, or HST, changed everything we knew about the universe. HST was effectively used to study the distant supernova in our universe that explained the fluidity of our space. This is to say, scientists employed supernovas to study the expansion of the universe. What they found out was completely opposite to what they knew about our universe. And let's just say, scientists were left completely dumbfounded and clueless. After all, the whiplash was monumental. Not to mention, this single discovery meant that astronomical studies had to be inherently rewritten and revised. Scientists had to look back at their theoretical studies and change everything on the basis of what the Hubble Space Telescope showed them. And there was no room for error of judgment. For the first time in the study of the universe, seeing was believing. It had turned out that gravity wasn't slowing the expansion of the universe at all. In fact, the universe was expanding at a higher acceleration than it had ever before. You heard that right. Ever since the universe's inception, the rate of expansion had only increased from its earlier data points. For the most part, this unexpected theory was hard to explain. Of course, gravity couldn't cause the faster acceleration. If anything, gravity should have fought valiantly to de-accelerate the rate of the universe's expansion. But by all accounts, gravity was rendered powerless. In fact, to this day, we don't know how or why the universe was expanding to astronomical degrees. As per theoretical knowledge, the expansion should have slowed down, unless and until there was an anti-gravitational force in the universe that was effectively overpowering gravity. And until the recent discovery of the James Webb Space Telescope, scientists were mostly of the opinion that our universe is a huge battlefield. Here's why you see after Hubble's discovery, the scientific world was in a crisis. Agencies like NASA wanted quick explanations for the unprecedented cosmic acceleration. Our first guess was that perhaps Einstein's theory of gravity isn't as accurate as we thought. As per the theory, we had started to recognize gravity as a distortion of time and space that is caused by mass and energy. In theory, gravity wasn't just a force, it could wrap around mass to push it or pull it. So if this theory stood correct, the universe shouldn't have been expanding at accelerated rates. Another thing that could explain the phenomenon was some energy fluid that hastened the expansion. Now there were a lot of contesting theories that came and went away. Nothing really stood its ground. Eventually, the possibility of falsifying Einstein also went away. Today, the only answer to Hubble's astounding discovery can be summarized in 2 words: dark energy. Yep, now you know why this throwaway word in science is so important. But you'd be surprised to know that we don't know anything about this force. None at all. The only thing we know is that it makes up the majority of our universe. It's almost frightening, but the normal matter just constitutes 5% of our universe. The rest is just dark matter and dark energy. This also proves Einstein's notorious cosmological constant. The way Albert Einstein explained empty space, it was always an entity with its own force. And as the universe expands, this force wouldn't change or get diluted even to the slightest. The end of cosmological constant. So how's this related to what the James Webb Telescope shows us? Why has our universe stopped expanding in the presence of dark energy? Well, scientists are still getting comfortable with the bizarre discovery. But if we had to look at the optics of the duel between gravity and dark energy, we might have an answer. The cosmological constant is the enigmatic force in space that can be substituted for dark energy. The scientific theory suggests that gravity and dark energy are always in a battle with each other. It's just about what gets the upper hand, what overpowers the other. Before our universe stopped expanding, it seemed like that dark energy was giving gravitational pull a run for its money. In doing so, our universe was expanding at accelerated rates. Now, this phenomenon has halted completely. Considering that our knowledge of space properties and dark matter was already profoundly limited, scientists have no trajectory to explain this disruption whatsoever. While NASA was already expecting anti-dark energy to emerge, this particular notion of physics wasn't anticipated in the current epoch we live in. By all means, the halt in the universe's expansion, as Brian Cox would put it, is entirely new physics. Of course, one simple and logical explanation could be that gravity is finally overpowering dark energy to stop the expansion of the universe. Because if our universe has a trajectory, it would have at least contracted to a considerable degree before the expansion stopped altogether. Or maybe gravity started to cancel the effects of dark energy out of nowhere. In either case, we need substantial observational and theoretical proof to justify if gravity is changing its properties. And well, that's one heck of a chore, because if there's anything we know about gravity, it's the idea that it has never changed. Yep, ever since the inception of the universe, gravity is constant. And so far, we don't have ample proof that there's a change in how gravity is interacting with the universe. This couldn't be more terrifying. The Big Crunch. But for better or worse, due to the theoretical works of scientists like Cox, we have some idea about the impacts of anti-dark energy. Call it a strategic foreshadowing or a shot in the dark. But a particular scientist was already preparing for the reversal of dark energy. Back in 2011, Brian Cox released his critically acclaimed book, Wonders of the Universe, followed by a TV series of the same name. This classic combination of the book and TV show did some wonders for the general audience who wanted to learn more about the universe in layman's terms. The series is highly enjoyable, but it also takes a dark turn when Cox and his co-author, Andrew Cohen, talk about the end of the universe. Alright, no one really wants to think about the apocalypse, but if our universe has stopped expanding and there's no going back, perhaps this is the right time to imagine the unimaginable. For starters, we know that time isn't linear, but then again, our existence is intrinsically tied to the universe. If it contracts and collapses, so do we. Since the universe has stopped expanding from what we could gather, that's the passageway for the sun to cool down. And in that case, we'd be witnessing the apocalypse in pitch-black darkness. Then, the universe would collapse onto itself, and we'd be lured into the single black hole singularity again. Yet, for this to become our fate, it will take 6 billion years or so. At least that's what Brian Cox theorizes. It's almost unironical. But this recent discovery means that most scientists are falling back to the ultimate fate theories that were previously considered untestable, or straight-up mythical. One important topic in physical cosmology is the ultimate fate of the universe, which primarily focuses on evolution and the end of time. In this emerging field, our theory of interest is called the Big Crunch, the moment when the universe stops expanding and begins to contract. This cosmological event occurs when the average density of the universe will be ample enough for the expansion to stop. While Big Crunch is heavily understudied, we can predict how the universe ends. You see, if the gravitational pull of the universe becomes ultra-intense, it will be able to cut through the space-time dimension. And in the blink of an eye, our universe will fall into a dimensionless singularity that marks the inception of the Big Bang. Yeah, theoretically speaking, we'd be right back to where we started, the beginning of the so-called eternity. Remember when we said we seem to go backward in time? This is precisely why. Whereas the Big Crunch wasn't ever discarded from astronomical studies, it wasn't exactly a very popular theory either. Now our data suggests that not only is the crunch a plausible theory, but we're also on the verge of universal recollapse. This means that we're nearer to Big Bang 2.0 than we had previously hypothesized. Cosmic time. When does the world end? It's almost frightening, but our affinity with the black hole singularity isn't a matter of billions of years. It's actually just mere millions. Cosmologically speaking, the recollapse of the universe is almost measurable in geological timelines as well. So yeah, while Brian Cox was right to theorize about the diminished role of dark energy, his timeline for the apocalypse was a tad bit off. If we strictly follow the linear laws of time, we could have thought about following the same trajectory as the Big Bang. Picture this. You're running a marathon from Park A to Park B. While in the middle of your run, the referee or whoever is controlling the race suddenly changes the rule of the race. Now, you're supposed to run back to point A, right where you started. Since you weren't at Park B yet, you'll run back to Park A. Should take the same time when you were running earlier. Sure, there might be some difference in speed here and there, but strictly on the basis of spatiality and time, your trajectory isn't changing, right? Following the same logic, if our universe is running backward and mimicking the events from its inception, then it should take us around 13 billion years to recreate the Big Bang. If only cosmic time was as simple as that. In a new study by scientists from Princeton University, it is revealed that the acceleration of the expansion is slowing down at exponential speeds, and its implications are going to be catastrophic. While the Big Crunch was a thing of the distant future, its real-time observational data isn't. In fact, the study was able to capture the possibility of the Big Bang 2.0 in dinosaur timescales. Yep, that's both interesting and terrifying. The report says, and we quote, "The time interval remaining before the end of acceleration is less than the time since the Chicxulub asteroid brought an end to the dinosaurs." Now, how long ago did all dinosaurs go extinct? All right, we won't ask you to live through another trivia question, so we'll just give you the correct answer right away. 65 million years ago. Yes, in one scenario, we're definitely living at the second origin of the universe. It might seem like 65 million years is a lot, considering our aggravated struggle with climate change and our planet's inadaptability. But any bets on survival hardly exist in binaries, not to mention 65 million years is absolutely nothing in the cosmic time frame. In certain epochs, it just amounts to a mere blink of an eye. It's also worth noting that a lot of scientists believe that Big Bang 2.0 will only happen after the collapse of life on Earth. Perhaps we'd prefer it that way. Yet so far, we don't have decent scientific data to back this theory up. Alright, we're not asking to lose any sleep yet, but we can't ignore the haunting facts about this discovery, mainly because it's not easy to detect rapidly changing cosmic events. Our biggest evidence in these unprecedented times is supernovas, or the echo of the Big Bang itself. Such cosmic entities aren't susceptible to change very quickly. Before they show any signs of cosmic transformation, it might be too late to do anything about it. Our only glimmer of hope in this scenario is the James Webb Space Telescope, which has been monumental in the up-close study of the Big Bang. With this groundbreaking device, scientists hope to track changes in the trajectory of distant objects that used to emit lights billions of years ago. The end of Big Freeze. While we figure out the logistical and feasible mechanism to study the contraction of the universe, certain predictions are based on our prior theoretical knowledge. What we definitely know is that our universe is never at a standstill. It either expands or contracts. In the case of the latter, gravity ends up dominating the universe. We can't be certain what happens to dark matter yet. Its powerlessness can finally put one popular theory to rest. If the universe never starts to expand again, the end of all life would be more catastrophic than the Big Freeze. Humans have long theorized that the universe will freeze to its death, but that was only a possibility when dark energy was expanding our universe at accelerated rates. Galaxies and stars were moving away from us. In other words, the universe was disappearing. Scientists expected that in some trillion years or so, the formation of stars will stop entirely as black holes latch onto any remnants of the universe. In this dark era, it was predicted that all energy in the universe will be evenly distributed. And of course, when we use the word energy, we're also talking about heat. So the final temperature of the universe would be close to zero, and everything would be just eternal darkness. Now the Big Freeze isn't a possibility, but let's just say we've dodged a bullet to stand in line for the next one. The Big Crunch is terrifying, yet it's our distant reality. Found this video informative? Give us a like and subscribe to our channel.